All right, great. So today I want to start the next big chunk of this course, which is to take what we've been doing for path integrals in quantum mechanics and then apply it to quantum field theory. Quantum field theory really go down as one of humanity's great discoveries, I think. And it's allowed us to probe nature on levels that we simply would not have been able to or even dreamed of previously. And while I would love to spend, as much time as possible exploring all its many delights, this is not technically a course on quantum field theory. And so I'm going to constrain myself to exploring a particular formulation of quantum field theory, which is the path integral formulation, which we're deriving from what we've studied in quantum mechanics and just straight up integrals coming forward. So we've actually done a lot of the hard work. We've developed a lot of the tools. We've done most of the heavy lifting in this. And so let's take what we've learned. Let's take these tools and apply it to quantum field theory. So before we get started with the actual details of it, I want to start by just establishing some notation, which is going to be useful for us. And the first one has to do with the signature of metric we're going to be working with. Now, depending on the text you're reading, you will encounter different signatures of the space-time metric, sometimes mostly plus, sometimes mostly minus. The quantum field theory texts tend to focus on a mostly minus signature metric. What this means is that, and we're going to be working primarily in three spatial dimensions, so 3 + 1 dimensional space-time. What this means is that inner products are going to be defined in a particular way. So suppose I have 4 space-time vectors. So these are what you would call 4 vectors in the language of physics. So these would be 4 vectors. Then we define the inner product between the 2 vectors as G mu nu A mu B nu, where G mu nu is a diagonal metric. It's a diagonal matrix, which will consist of a -1 in the 0, 0 position, a +1 in the 0, 0 position, and then -1s down the diagonal from 1, 1, 2, 2, 3, 3. So what this means is that if I expand this directly in terms of the components of the vectors, this is A0, B0 minus A dot B, where now this dot is a standard dot product. Okay. And this dot on the left-hand side here, this is an inner product in 4-dimensional space-time. And I define it via that relation. And this here is a dot product with 2, 3 vectors. Okay, so that's the first bit of notation that we need. The second bit of notation has to do with how we define Fourier transforms. So we're going to define the Fourier transform as follows. So this is point 2, this is Fourier transform. So I'm going to define the Fourier transform in 4 dimensions as follows. Given a function f of x, I'm going to define its Fourier transform f tilde of k, and f tilde of k is going to be defined as the integral over 4-dimensional space-time of f of x e to the plus ikx. Okay, in principle, I should write down dot kx, meaning this dot, but I'm going to take the liberty of abusing notation and just write down an ikx. So typically when I leave out the dot there, I mean a 4 vector product. And the inverse of this Fourier transform, so given f tilde of k, I can reconstruct f of x as the integral of t4k, so integral over momentum space, over 2 pi to the 4. That's my metric, that's my measure on the integral, f tilde of k e to the minus I kx. Okay, so these are my definitions. These are going to be my definitions for Fourier transforms. That we're going to be using as we go forward. Okay. So now I want to take what we've learned in quantum mechanics and apply it where we were dealing with a single degree of freedom that we called Q of T. And we want to apply it to an infinite number of degrees of freedom, which I'm going to call, phi. So we're going to start off. So quantum mechanics, and we're going to quantum field theory. And this is going to involve taking our single degree of freedom Q of T and extending it to a field phi of x like that, which is going to mean phi of a vector, a 3-vector x, as well as a time. So phi of x t. So how do we do this? Well, in principle, what we need to do in order to make this transition from quantum mechanics to quantum field theory is to take space-time, divide up the continuum function phi into a discrete set of functions phi, let's say n, which are associated with discretizations of derivatives and integrals on this lattice. Then we repeat everything that we did in the quantum mechanics case for the discrete variables phi sub n. And then we take the limit as the density of lattice points goes to infinity, so that we re-arrive at the continuum. That's what we would do in principle. In practice, basically it all comes out in the wash. And the generalization from quantum mechanics to quantum field theory is pretty much exactly how you would expect it to be if you just did the naive thing. There are, of course, some subtleties that more or less stumped the development of quantum field theory for a number of years, and it stumped the best, brightest minds of their time, namely Heisenberg and Dirac and Feynman and Schwinger and Tomonaga, and resulted in the program that we call the renormalization program, which, circa 1970s, we finally understand due to the work of Wilson and Kadanoff and people like that. But again, we're not going to be spending too much time focusing on these subtleties. They will come up at some point where you will see infinities arise in places that we think that they shouldn't, and we'll explain away these infinities in a hand-waving way, with the knowledge that if you so choose, you can certainly make them more rigorous. Okay, so the moral of what I was trying to say is that don't worry too much about the subtleties. They do all come out in the wash, and we're just going to proceed again with the naive thing, with the understanding that what we're trying to do here is build some tools to solve some physical problems. Okay, that said, we need to say a few things about functional integration, because functional integration is going to play a crucial role in this path integral version of the story that we're building. And functional integration starts with the Gaussian integral. Okay, so I'm going to start from something that we are well familiar with, which is an integral of the form integral from minus infinity to infinity of e to the minus ax squared over 2 dx. Okay, this is certainly an integral that you should have seen before. If you haven't seen before in other courses, you know, I've certainly intimated that this is something that's absolutely standard in what we're trying to do here. Well, it's quite straightforward to compute this integral. Basically, you compute the square of the integral, convert to polar coordinates, carry out the integral on the 2-plane, and take the square root of it. And when you do that, you'll find that this is just 2 pi over a to the half. Okay, so this is the absolute basis from where we're going to start off. Okay. Given that we've already developed a lot of the tools for at least a philosophical attack on path integrals, this is where we're going to start off with for quantum field theory. Now, given this single Gaussian, I would like to take the product of n such integrals. Okay, so let's generalize this. In fact, let me, okay. So let's call this the single Gaussian integral. And again, let me recolor this thing. All right. So now let's consider a generalization that's going to be multiple Gaussians. And we'll start by taking the parameters like this A here. We're going to take these parameters and call them AI. So there's n such AIs. And I'm going to take all of them to be positive without any loss of generalization. And I goes here 1 through to n. Okay, so the integral that we want to consider here is an integral that goes integral from minus infinity to infinity all the way through to the nth such integral. And we're doing an exponential, and it's minus a half, which is this factor of a half, minus a half sum over I AI xi squared. So this is the Gaussian integral that we want to do. And we want to do it with respect to dx1 all the way through to dxn. Well, that's just the product of n of these integrals that we had before. So I can write it down immediately what the answer is going to be. So it's going to be 2 pi to the n over 2 over the product of the AIs. So it's product from I equals 1 to n of AI raised to the half. There's a reason I split this up this way, which is that we're going to be considering variants on this particular theme, where we're going to take these n Gaussian integrals and we're going to do things to them, add cross terms, etc., etc., and it's going to become less and less. Well, it's going to become more and more complicated to write this down. So let's develop a let's put this in a more palatable form. So we can do this by making a definition. So to make this more palatable, let's make the following definitions. So I'm going to define a vector x, which will have components x1 through xn, like such, and a matrix A, which will have diagonal components A1 through to AN, like this, and zeros everywhere else, like such. Okay, in which case I notice the following. This term here the sum, sorry, let me close the whole sum. The sum of AI xi squared is nothing but the inner product of xi with ax. And by this, I mean the matrix product, which means you take x, you transpose it, then you multiply it with a times x. On the other hand, this quantity in the denominator here, the product of all the AIs, sorry, this should be, let's do that again. In case it wasn't clear, that's what I mean there, right? You take the product of all the AIs and take the square root of that. This guy here, the product of all the AIs, is nothing but the determinant of the matrix A. Okay? Which means that my multiple Gaussian integrals can then be written in the following way. It means that I can write the integral, and my integrals will run from minus infinity to infinity, yeah, of the exponential minus a half of x inner product ax dnx is 2 pi to the n over 2 times 1 over the square root of the determinant of A. Okay. Can everybody see that?
Yeah.
Okay. This statement holds for any diagonal matrix A, which means that it also holds for any symmetric, real, positive, non-singular matrix. So this holds for any symmetric, positive, real, and non-singular matrix A. That's because I can always put any symmetric, real, positive, non-singular matrix A into a block diagonal form, in which case this result will hold. And we can make it a little bit neater as well if we define, we can tidy this up a little bit more by defining if we define dx to be dnx times 2 pi to the minus n over 2. In other words, we take this factor of 2 pi to the n over 2 on this side and we combine with the dnx and just call that dx. Then we get the following. Then we find that the integral of e to the minus 1/2.
I have a little question.
Go for it.
So this relation is supposed to hold for any symmetric, positive, and all these A. Let's just say that A is symmetric and obviously following all the properties as well, but it has some cross terms like non-diagonal terms, but still symmetric. In that case, we'll introduce some linear terms in the exponential, and then I guess the integral will change, right?
Yeah.
So how would the relation still hold?
Let me show you, or rather, you show you. So
Okay.
here's an exercise. And the exercise is precisely what I think Nitin is asking, which is what happens when you have cross terms, right? Yes?
Yeah.
Okay. So suppose I have cross terms, and let's just write it in the most general form we can. Okay, so suppose that I want to do the integral e to the, and I'm going to write it out in the following way, minus a half. So a half of x ax, so there's my quadratic piece, plus bx, there's my linear piece, plus some constant c. Okay, so that's the integral we want to do. And we want to do this with respect to x defined in this way. Okay, I want you to show that you would be able to write this thing as a half of b in a product with A inverse A inverse B minus C, so that's e to the that, times determinant of A to the minus a half. Does that answer your question?
I'm not sure. I'll have to do the calculation and understand.
Okay. All right. So that's what happens if you have a real symmetric positive non-singular matrix. What about if it's not real? But it's generalization of that to complex variables or to complex valued things if it's a Hermitian matrix, right? So the question is, what about if A is Hermitian instead? Okay, so let's try and answer that. And we'll see that there is actually a change. So if A is Hermitian instead of symmetric, real symmetric, then there, the Gaussian integral that we start off with is the following instead. So here, let's write it like this. If instead we start from the following Gaussian integral, again, integral is over minus infinity to infinity, and I'm doing two Gaussian integrals now. And I'm just going to use shorthand and say that I'm considering the integral over dx dy, e to the minus a times x squared plus y squared dx dy over 2. Then this integral you can show evaluates to 2 pi over a. Okay. So now let's go to complex coordinates. So I should emphasize that this integral This integral is done on R2. So now I want to change coordinatization on R2 from X and Y coordinates to complex coordinates Z and Z bar. So Z is going to be defined as 1/√2 of X plus I Y, and Z bar will be the same with a minus sign here. Okay, in particular, going to complex coordinates means that my integration measure dx dy can be written as minus I dz bar dz. Okay. Just make sure you can show this. But what this means in terms of my Gaussian integral is that the integral over R2 of e to the minus ax squared plus y squared over 2 dx dy can be written simply as the integral now over complex plane of e to the minus a z bar dz dz bar over I, and this is just two pi over a. Or in other words, the integral of e to the minus a z bar dz over 2 pi I to the half dz bar over 2 pi I to the half is equal to 1 over a, which I get by taking the factor of 2 pi from the right-hand side and splitting it equally between the dz and dz bar on the left-hand side, as well as the factor of pi in the denominator. So now we're in the position to say that if A is a positive definite Hermitian matrix, and we define dz as dnz over 2 pi I to the n over 2, then we can immediately generalize our multiple Gaussian integral, this guy here, to a Hermitian matrix. Then we find that the integral over C of e to the minus z az like this, dz dz bar is equal to 1 over the determinant of z. And just unpacking this, by this I mean simply z bar az, and this here, this dz here, will mean d to the n z times 2 pi I to the minus n over 2. Right. Okay. So far, everything that I've said holds for straight up real and complex integrals. Okay, or one-dimensional integrals and two-dimensional real integrals. All I've done is I've reorganized things, taken care of some of the bookkeeping, but nothing here is particularly deep or conceptually difficult to understand. Now I'm going to make a leap of faith, and I'm going to assume that you will jump with me, and assume that everything that I've just said, which holds for finite dimensional vector spaces, will continue to hold for an infinite dimensional functional space. In this case, so let's make a note of that. So now let's make an assumption . So then I'm going to define phi of x, and x here means a full vector x mu. So this is just x mu. To define the inner product between phi of x and phi of x to be the integral over space of phi squared of x. Okay, and the generalization of what we just did for the real variable will read the integral over phi's of e to the minus a half phi a phi, and this will equal to det of a to the minus a half. Okay, the only thing here is that while we did everything for finite dimensional vector spaces where a was a finite dimensional matrix, an n by n matrix, here I'm gonna, when we go to a function space, this a here could possibly be a differential operator. And this is going to be important. Okay, so this is what happens for a real scalar. So this phi here is a real scalar. And for a complex scalar, which we're going to encounter, the following will hold. Very similar to what we found for complex variables. And the reason why we want complex scalars is because complex scalars will correspond to charged fields. There we will find that the integral over phi bar over phi of e to the minus phi a phi is just 1 over the determinant of the operator a. Okay. Any questions? So this is going to be absolutely key in getting us to be able to compute the path integral for these scalars. Our goal in this section is going to be to compute Green's functions for these kinds of scalar fields, so real neutral scalars or charged complex scalars. So let's start off with the simplest thing possible, and we'll start off with a free massive scalar. The Lagrangian for the Lagrangian density for such an object is, we'll call L naught, and L naught is going to be a half d mu phi, d mu phi, by which I mean here an inner product between d phi and d phi, a four-dimensional inner product between d phi and d phi, minus m squared phi squared. Okay. The corresponding vacuum to vacuum amplitude, again, just building on what we did for the quantum mechanics case, is given by what I'm going to call Z naught, which is going to be a functional of some source function J. And this is just going to be the integral over phi of e to the minus I times the integral over four-dimensional spacetime of a half phi box, which is the D'Alembert operator, d mu, plus m squared minus I epsilon phi minus phi j. Let's close brackets there and close brackets there. So let's unpack this a little bit. This is the D'Alembert operator. This is a regulator term that I know I'm going to have to add because of the problem that we encountered with carrying out a Lorentzian, a non-Euclidean integral previously, where I had a pole that lay on the integration contour. This is a source term, which I'm adding because I know that I'm going to have to take functional derivatives of this vacuum to vacuum amplitude, Z naught, in order to build up correlation functions. And the interpretation that we gave to this from investigating the quantum mechanics case was as a source term, or something that appeared on the right-hand side of the equation of motion. And the reason why this is in this form here is because of integration by parts. So this phi is in this position because I integrated by parts. Okay, so I write it as phi, some operator, in this case, box plus m squared minus I epsilon times phi minus phi times j. Are we clear?
Yeah.
Good. All right, so I'm going to stop there today, and then we'll pick it up on Wednesday by showing how to compute the 2-point function for, well, the 2 and the 4-point functions for this theory. This m here, by the way, is the mass term. Okay, very good. So let's stop there. All right, thanks, guys. I will see you again on Wednesday.
Thank you.
Thank you.